Okay, this is a recording of the lecture for Chapter 13 on chemical equilibrium. First of all, I'd like us to think about this example while we're trying to understand what chemical equilibrium is. Think about the guests in a hotel or the number of people in a hotel. If during a day, if we look at a hotel, we have a certain number of people checking in, and then we have a certain of people checking out. So the number of people that are in the hotel at any given time depends on the number that check in and the number that check out. If the number of people that check in is the same as the number of people that check out, we do not have a change in the amount. So the number of people that are in the hotel, we just have a change in the identity of the people in the hotel. I want you to keep that in mind when you're thinking about a chemical equilibrium because it is very similar to that. In a chemical reaction, when I have both reactants and products, a reaction is going to proceed until it reaches what we call a chemical equilibrium, where you have the same number of reactants going to products as you have products going to reactants. Let's look at it a little more closely. Here's an example of a chemical reaction, and up until now we've only really talked about one direction, which is called forward direction, in which the reactants are written on the left side and the products are written on the right-hand side with an arrow pointing from the reactants to the products. This is called the forward direction. However, a reaction can also proceed in what we call the reverse reaction, so from the products towards the reactants. This is called the reverse reactant. Or the reverse reaction, in which the products of the forward reaction now become the reactants, and the reactants of the forward reaction now become the products. So a reaction, the way it's written, has a forward rate from N2 plus 3H2 going to 2NH3, that's the forward rate. However, it can also proceed in the reverse or the opposite direction from 2NH3 breaking down to form N2 plus 3H2. The forward and the reverse reactions are denoted with an arrow or with a double-sided arrow like here, or an equal sign with two arrows pointing in either direction. There's several different ways you can do that, but as long as you have two arrows pointing in either direction, that tells you that this reaction is reversible. It can go in one direction and in the other as well. Once equilibrium is attained, though, we notice that the concentration, so the square brackets in these chapters, if you see square brackets, is going to denote concentrations. Concentrations of reactants and products, they no longer change. Let's look at this reaction kind of in a graphical representation. Here's my concentration versus time. And if I monitor the concentration versus time of all three of these species, I find, for example, that at time 0, the blue is my nitrogen and the green is my hydrogen. At time 0, my purplish, pinkish curve, NH3, is 0 because at the very beginning I have no NH3 present. I only have a certain amount of nitrogen and a certain amount of hydrogen, about 3 times as much hydrogen as I do nitrogen. But I have no ammonia, and therefore that concentration is 0. As time progresses, however, this reaction is going to occur. My nitrogen and my hydrogen are going to react with each other to produce some ammonia. So I'm going to see an increase in my ammonia concentration and a decrease in my hydrogen and nitrogen concentrations. The forward rate, so how fast this reaction is going to happen in the forward direction, will be determined by the concentrations of these species. And at the beginning, it goes faster, because there's nothing to hinder, so there's no product. There's only reactants. As they react, however, the rate slows down a little bit, and the backwards or the reverse rate speeds up because now I have some NH3 occurring. And as you can see, after a little bit of time, my nitrogen concentration levels out, so does my hydrogen concentration and my NH3 concentration. These straight lines here represent or denote the fact that none of these concentrations are changing anymore. This is what we call an equilibrium state for the reaction, where once equilibrium is attained, the concentration of my reactants and the concentration of my products are no longer changing, or they appear not to change, which means that the rate, how fast the reaction is proceeding in this direction, is the same as how fast the reverse reaction is proceeding, so in the opposite direction. The rate of the forward equals the rate of the reverse. I am combining my reactants to form my product, so N2 plus H2 to form NH3, as fast as I am taking NH3 and breaking it down to form N2 and H2. Note that this equilibrium is a dynamic equilibrium. Remember this word. It's a dynamic equilibrium, meaning it's not that the reaction completely stops. Once it reaches equilibrium, then that's it. I have nothing else is going on. In fact, what I do have is both the forward reaction and the backward reaction, the reverse reaction, are occurring at the same time, and they keep occurring. What happens is that the apparent concentration of my reactants and the apparent concentration of my products is not changing. It's staying constant because as soon as I'm making, let's say, ammonia, as soon as I'm making it, I'm breaking it down by the opposite direction reaction. So that makes it not a static value, but a dynamic value. It appears that it is not changing, but I'm making it because I'm making it as fast as I'm breaking it down. Same thing with my reactants. I'm combining them to form my product as fast as the product is breaking down to make them back. And therefore, those concentrations do not change overall. That is why we call it a dynamic equilibrium. Phase changes also have the equilibria established. They're not chemical because we're changing phases, but they also reach equilibria. Remember, in the previous chapters, we talked about the equilibrium that is established between a liquid and the gas above it. And that is a phase change equilibrium. It's the same substance. I have no chemical reaction occurring, but I have an equilibrium that is being established between the gas molecules above a liquid and that particular liquid. And in the equilibrium, once again, it's a dynamic equilibrium because I am helping a certain number of gas molecules to escape in the gaseous phase, and as many molecules are returning from the gaseous phase into the liquid phase. And so you get this cycling occurring, but that cycling is equal in both directions, and it keeps concentrations appearing not to change. they don't change, but it's not the same molecules over and over. Just like here, it's not the same guests stay in, but the number of guests doesn't change. Similar to the idea here, it's not the same molecules of N2 that are constant, or H2, but it's the recycling of those that keeps the overall concentration of the reactants and products not changing. What happens, though, to the reactions before we reach equilibrium? How can we know what the status of a reaction is before we reach equilibrium? For that, we look at an entity called the reaction quotient, and we denote it with a capital Q. In this particular reaction, it's a generalized reaction. You can have all 4 or more species or less, it doesn't matter. But in a general reaction like this, where I have A moles of A plus B moles of B, giving me C moles of C plus D moles of D, I write the equilibrium quotient in this manner. I have the product of the concentrations of my reactants raised to the power of the molar coefficients in front of them. So I multiply the concentration of C raised to the power of the molar coefficient that's in front of it, multiplied by the concentration of D, of my product, D, raised to the power of the coefficient that's in front of it. Now, if I had another product here, another species here, I would multiply it by E, let's say, concentration of E raised to the E power, whatever the molar coefficient would be in front of that. All of that is divided by the concentration of my reactants, multiplied and raised to their molar coefficients. A, my concentration of species A raised to the molar coefficient of A, times the concentration of my reactant B raised to that power, the molar coefficient of B. I can also, for gaseous reaction, I can also do the same thing, but instead of molar concentrations like I have written here, I would use the partial pressures of each gas raised to the same power, raised to those molar coefficients. We can write it both ways. For this reaction then, that we were talking about earlier, the formation of ammonia, I can write, here's the example of how I write my reaction quotient. I will take the concentration of ammonia raised to the second power, because that's the molar coefficient in front of my product, divided, and I don't have any more products, so that's only one appears, divided by the product of my first reactant, the concentration of N2 raised to the first power, because I have 1 for molar coefficient, multiplied by the concentration of H2 raised to the third power, because that's the molar coefficient in front of H2. This is how we write a reaction quotient. It's a quotient, it's a fraction, a division, if you will, of my concentration. So the product of the concentration of my reactants raised to their respective powers divided by the product of the concentrations of my reactants raised to their respective powers. I can write a quotient and I can substitute values here for at any point in the reaction as it is proceeding. If I know the values of each of the products and the reactants, I can then calculate this Q at any point in the reaction. If the reaction reaches equilibrium, then my Q, my reaction quotient, equals K, a constant, because as we said earlier, these concentrations do not change any longer, so I get a constant at equilibrium. This value of Q is denoted with K at concentration. So K is a special case of Q, and it's only true, this is only true at equilibrium. At any other point, Q is not equal to K. But once my reaction reaches equilibrium, these two, so Q becomes K. And the concentrations of the reactants and products are not changing anymore. K, as I said, is a constant at equilibrium for a given temperature. This is very, very important. K is dependent on temperature. Therefore, at different temperatures, K will have a different value. We speak of K being a constant at equilibrium for a particular or given temperature. If K, or if the temperature changes, then K will also change. It doesn't matter in which reaction you start first. You can start with the nitrogen and hydrogen first at a certain at a particular temperature and allow that reaction to go to equilibrium. Or you can start with ammonia gas at the same temperature and allow it to reach equilibrium. You will come up with the same value for K in either direction. It doesn't matter if you're proceeding in the forward direction or in the reverse direction. The value of K for both the reverse and the forward reactions is the same at a particular temperature. That is called the law of mass action. So the law of mass action says that the K, the equilibrium constant, is constant for a particular temperature, and it doesn't matter if you start basically if you proceed in the forward direction or in the reverse direction. So let's look at the special case for Q at the equilibrium constant. This is a constant, so K is a constant which expresses the relationship between our reactants here and our products and their concentrations once the system reaches equilibrium. K is not constant unless it reaches equilibrium. If it isn't at equilibrium, then K is Q and it's always changing. Once it reaches equilibrium, then Q becomes K. We write the value for K the same exact way as we do for Q because K is a special case for Q. So here's the same formula that we just talked about. C raised to the, to be, I guess, easier for you to remember, P comes before R, so products over reactants. I don't know if that will help, but I have the concentration of my first product raised to the molar coefficient times the concentration of my second product raised to its molar coefficient divided by the product of the respective reactants raised to their molar coefficients. And is also equal to the rate, so the little k here is the forward rate, the rate of the forward reaction divided by the rate of the reverse reaction. The rate is the speed, okay? The speed by which the forward reaction proceeds over the speed by which the reverse reaction proceeds. Here's an example of another reaction. Once again, if I have hydrogen plus iodine giving me hydrogen iodide. If I proceed in the forward direction, I will, after a while, reach, if I monitor the concentrations, the rates even, so here's my reaction rate and here's versus time, it will reach a certain value and then will not change anymore. It will become constant. It doesn't really matter if I even start in the backward reaction. This will increase so this is my forward rate. This will decrease. My backward or reverse rate will increase until they both hit one constant value, and this is my equilibrium state. Let's look at K and figure out if we can tell if we have a small value for K or a large value for K, whether that tells us anything about the reaction itself. If I have a small value for K, so K is a lot smaller than 1, if by looking at this quotient, if K is smaller than 1, that means that the bottom number, the denominator, is much larger than the numerator to make it smaller, much smaller than 1. What is in the bottom, or my denominator, is the concentration of my reactants. And the top number, the numerator, is the concentration of my products. So if I have a large denominator to give me a small value for K, that means that I have a lot of reactants, or a lot more reactants than I do products at equilibrium. If I have a small K, that means that reactants are favored, meaning that this reaction is not going to proceed very far towards the products in the forward rate. My reactants like to be in their reactant state. They do not like to react much with each other to give me product. That scenario gives me a small number for the concentration of my product divided by a large number for the concentration of my reactants, giving me a K that is a small number. What happens when I have a large K? Well, the opposite is true. If I have a large K, that means my numerator is much larger than my denominator. How do I get a large numerator? Well, if I have a lot of product made, or a lot more product than I do reactants, which means that this equilibrium, we call it, lies far to the right, meaning it favors the products. By favoring the products means that it makes a lot of product, versus favoring the reactants, which means it makes more reactant, but it doesn't consume the reactants. So therefore, to have a large K, a large value for K, I need to have a lot of product up on the top, and therefore my products are favored. I have more products than I have reactants at equilibrium. I should be able to look at the value for K, and I should be able to say which direction I am favoring, whether I'm favoring the reactant side or the product side as it's written. A small value for K means that I have a lot of my reactant, means that the equilibrium lies to the left side on the reactant side. If I have a large value for K, as it's written, I favor my products, meaning I will have a large number or a large concentration of my product as opposed to my reactants. Now notice that the value of K does not tell us anything about how fast the reaction reaches equilibrium. You can favor the products, but that is a different part of chemistry that studies the rate of reactions. That's called kinetics. You can favor the reactants, meaning you can have a large K, but it might take days or years for the reaction to reach equilibrium. K, therefore, how big or small it is doesn't tell us anything about how fast the reaction occurs. It just tells us that the reactants or the products are favored over each other. All the equilibria follow a certain set of rules. The first one is that the equation must be balanced, and you can see why that is because the molar coefficients appear up here on top, and so if you don't have a balanced chemical reaction, you will have the wrong numbers for the powers that go with each concentration. Therefore, the reaction or the chemical equation must always be balanced. That's the first thing you need to look at, is if the reaction is balanced or not. The second, I have two ones here, but the second rule is that liquids, so this is L for liquid or S, liquids or solids do not appear in the equilibrium expression if we have what are called a mixed phase heterogeneous equilibria. We are going to ignore what has an L or an S. Because we use relative terms, those drop out of the expressions because they're actually equal to 1, or we make them equal to 1 instead of a different number, so we cancel them out. This is also a reason why these values, even if they are in concentrations, do not have units, and so the equilibrium constant doesn't have a unit associated with it because they're not absolute values, they're relative values. They're divided by another value, a certain value for concentration. And so if you have a concentration divided by a concentration, it gives you a unitless number here, a unitless number here, etc., etc. So we don't have units for the equilibrium constant. Remember, no liquid or solids appear in my equilibrium expression or my Q, my quotient either. I can have an infinite number of stable concentration sets. Even if I just change the temperature, I will have a different concentration of my reactants and my products, giving me a different combination, giving me a different K at different temperatures. If I don't change the temperature, but I change the concentration of one or the other of these species, it's going to affect the forward and the reverse rates, and therefore my reaction is going to proceed in one way or another to change the rest of the concentrations, and therefore I will have a new stable concentration set. You can think then you can change concentrations an infinite number of times, giving you an infinite concentration set. If the concentration of everything is constant, then my system is in equilibrium. We talked about it being a dynamic equilibrium in which the concentration remains the same, but it's not the same molecules. They are just constantly being recycled. It's just the concentration overall of that species remains constant. If a change is made to the system will shift to a new stable set of concentrations. So 2 and, well, it'll be 3 and 5 will go together. These two values will go together because if I change the system an infinite number of times, the system will shift to a new stable set of concentration. Therefore, I have an infinite number of concentration sets. And we'll talk about this towards the end of the lecture when we talk about Le Chatelier's principle. How do we write equilibrium constant expressions? I will have a video made of these problems, and I will actually post the link right here. So as you're looking at this, you can click right on the link and it would open up the YouTube video on how to do all these. So watch for that. Now here's an interesting thing that we can do mathematically with the equilibrium constant. Let's look at this particular reaction. If I have PCl5 breaking down to give me PCl3 plus Cl2 at a certain temperature, here's my equilibrium constant for this reaction. The concentration of my PCl3 Now note that this is all 1-to-1 ratios because it's a balanced chemical reaction. 5 chlorines, 5 chlorines, 1 phosphorus, 1 phosphorus. All my molar concentrations are 1. So my powers here are all going to be 1. The concentration of PCl3 multiplied by the concentration of my chlorine divided by the concentration of PCl5. And it will have a value of 0.05. In this case, you are given the value for K. Some other cases you might have to calculate this value if you're given these values. We'll do some problems with that. But in this case, you're given 0.05 as the value for K at equilibrium for this particular reaction. Now what happens if I reverse this reaction and I make my products, I make them the reactants? PCl3 plus Cl2 giving me PCl5. Once again, it's balanced. So I write a new concentration, equilibrium constant, with calling it K prime. It will be equal to, once again, product over reactant. Concentration of PCl5 divided by the concentration of PCl3 multiplied by the concentration of Cl2. If you notice, these two values or these two expressions are the reverse of each other, and therefore my new value for K prime is going to be 1 over 0.05, which was the value of K, 1 over 0.05. So anytime you take a forward reaction and you flip it to calculate the new equilibrium constant, all you have to do is take the old constant and do the reverse. So take 1 over that old constant to get the new equilibrium constant for the flipped reaction. What happens if I multiply the reaction by a particular number? Here's one reaction where I have calcium sulfate solid breaking down to calcium ion in an aqueous solution plus sulfate ion in an aqueous solution. Notice that it's balanced. All of these, I don't have to write them, but I wrote them to show the difference between these two equations. All the molar coefficients here are 1. So if I write this constant, equilibrium constant here, note that I don't have my solid in this particular expression, but it will be the concentration of my calcium, my first product, multiplied by the concentration of my sulfate, which is my second product. And normally we would have a quotient and divided by the concentration of my reactant, but because the reactant is a solid, it doesn't appear. It would be divided by 1 because the solids and liquids are 1. That's their concentrations. So this is my equilibrium constant for the first reaction. Now what happens if I multiply everything by 2? And remember, if you multiply any of these pieces by 2, you have to do the same thing to all the rest of them in a chemical equation. So if I multiply the concentration of calcium sulfate by 2, I have to multiply my calcium by 2, I have to multiply by my sulfate by 2 as well. The new equilibrium constant then, K prime C, is equal to the concentration of calcium, but now it's raised to the second power because I have 2 instead of 1, multiplied by SO4 2 minus raised to the second power. If you see then, if you compare these two, what's the, I guess the relationship between these two is that K prime C is equal to the Kc raised to the second power. If I'm given Kc, which here's the value for Kc, all I have to do to calculate K prime C then is to raise this number to the second power. So square it, and it gives me this value for the reaction where I doubled everything. I multiplied it by 2. So if I flip the reaction, I will take to calculate the new equilibrium constant, I do the reverse So I take 1 over the old K, equilibrium constant value. When I multiply or divide, I guess I could divide, you would raise this to the 1/2 power. If I divided it by 2, let's say, to the 1/2 power instead of second power. But I multiplied it by 2, you raise it to the second power to find the new K prime C. We will do some calculations with those as well. Now I can use the reaction quotient Q that we talked about to predict in which direction the reaction is going to proceed. If I know the value of K for a reaction, and I can figure out what the value of Q is at a particular point, I can compare Q, my reaction quotient, to K, the value for the equilibrium constant, and I can tell which direction the reaction is going to proceed, whether it's going to proceed in the forward direction or in the reverse reaction, the reverse direction. Here's the rules. If my Q, so if the value for Q is smaller than the value for K, the reaction will proceed to the right. More products will be formed. If my Q is larger than K, the reaction will proceed to the left, which means more reactants will be formed. Note that this got nothing to do with the K value being larger than 1 or smaller than 1, so a large K or a small k. This does not have anything to do with that. This, we are comparing the value of my quotient to the value of K to determine in which direction the reaction is going to proceed. So if Q is smaller than K, the reaction will proceed to the right, making more products. If Q is larger than K, the reaction will proceed to the left instead, making more reactants. If Q, this is my last possibility, if Q is equal to K, then the reaction is at equilibrium and my rates are going to be the same. So the reaction is going to, the rate of the forward reaction is the same as the rate of the reverse reaction. Here, if Q is smaller than K, the forward reaction rate is faster than the backward reaction rate. So that's why I'm going to keep proceeding to the right till those rates equate each other. In number 2, when Q is larger than K, the reaction will proceed to the left instead, which means the reverse reaction rate is larger than the forward reaction rate, and the reaction is going to keep going until those rates become equal again, and the chemical equation is now at equilibrium. Here's a problem on how to do that, and I'm going to once again make a video for this and have the link here so that you can look at this problem, click the link and watch the video, and it's fresh in your mind and you don't have to keep going back and forth between these two. But I will show you how to calculate the reaction quotient and then compare it to this is the K value, compare it to this value and figure out which direction this reaction is going to proceed. Okay. Now, I mentioned that we can write equilibrium constants for only 2 physical states. For aqueous solutions, where we deal with concentrations, square brackets denote concentrations, but we can also write them for gaseous compounds, so for gases. In that case, we write an equilibrium constant calling it Kp, where instead of using concentrations, we use the partial pressures of each gas. This is much easier for us to do because it's easier to measure the pressures of each gas than to measure their concentrations. Now these two, I can express them either way. I can express, so if I have this reaction in which all of my species are in the gaseous phase, I can express the equilibrium constant as a function of the pressures of each gas, but I can also express it as concentrations of each species. This would be Kc and this would be Kp, denoting pressure, and C denoting concentration. Kc and Kp are not equal, but they are related. I am not going to work out how they are related here. You can read about it in the book if you're interested. You don't need to know how the derivation goes, but this is the formula you will need to know that relates the equilibrium constant in the pressure form to the equilibrium constant in the concentration form. So Kp is equal to Kc multiplied by RT raised to the delta N. Now, if you follow the derivation, you would know that what these are. N is the number of moles, and I'll talk about it in a little, I'll hold off, I'll talk about this last. But R is the gas constant, the ideal gas constant. We used this extensively in chapter 8 when we dealt with gases. And the T is the temperature. Therefore, so in Kelvin, I have R being the gas constant and T being the temperature in Kelvin. Delta N is the change in number of moles. And how do I calculate this? I, of course, have to have a balanced chemical equation, but it is the change in, so the difference between the number of moles of gas between products and reactants. And it's given by the sum of the moles of products minus the sum of the moles of the reactants. That's why I have a change. I look at it for this example for here. I have my products are 2, and so 2 moles. My reactants are 3 plus 1 mole, 4. So the change in N would be 2 minus 4 would be minus 2. Therefore, the Kp for this reaction would be equal to Kc multiplied by RT raised to the minus 2 value. I will do, once again, I will do this problem separately, and I will have the link here so you can see how that is done. But just notice that for calculating delta N, you take the number of moles, the total number of moles of your product, and you subtract the total number of moles of your reactants to find the delta N. And it can be negative, and that's okay. Notice that if the delta N, so if the number of moles of both sides are equal, delta N is 0, which makes RT raised to the 0 power, makes this 1, which means that Kp and Kc are the same. That's the only time they are the same is if there is no change in the total number of moles of either side. So if the moles of NH3 were 4 here and the total number of my reactants was 4, that change in moles would be 0, which would make RT raised to the 0 power, which means it's a 1. Kc times 1 is Kc, and therefore Kp would equal to Kc. That's the only time these two values are the same. If the number of mole changes, delta N is not 0, and therefore these will be slightly different. Here's other problems that I'm going to work out on how to write equilibrium constant expressions and how to calculate an equilibrium constant value when you change the reaction, if you have it divided by 2, for example. here's another slide with how to do equilibrium constant calculations, and I will show you how to do them, whether it is to calculate the K value for the reaction if you're given concentration of all your species, or if you're given a value for K and values for two of your species and calculating the other, etc., etc. So I will work these problems in a separate video as well and put the link here, so watch for that. Now let's talk about the last part of the chapter 13. Let's talk about Le Chatelier's principle and the change. If you remember back a few slides when we talked about the rules of all equilibrium have to follow, and one of them was that if we make a change to the system, the equilibrium is going to shift in such a way that it will reach a new state with new concentrations, a stable set of concentrations. So if I disturb a system at equilibrium, now Q is not going to be equal to K anymore. Therefore, I will establish a new equilibrium with different concentrations. Therefore, my equilibrium shifts. How can I disturb a system? There are different ways that I can do that. I can change, remember square brackets denote concentration. I can change the concentration of either my reactant or my product. I can add more product or remove product. I can add reactant or remove reactant. That will favor one of the rates, the forward rate or the reverse rate. And it will shift until, once again, the forward and the reverse rates are equal to each other. I can change the pressure, especially if I'm dealing with gaseous systems. I can change the pressure, and I can change the temperature. I can add heat, I can remove heat. So if I have an exothermic reaction, that's going to act differently than an endothermic reaction if I add or remove heat. I can do a number of different things to disturb a system, but in every time I disturb it by whatever I do to it, a new equilibrium will be established because the equilibrium is going to shift in a particular reaction or direction. Le Chatelier's principle, named after the guy who came up with this idea, the Le Chatelier's principle states that if you disturb a system at equilibrium, the reaction is going to shift in the direction that opposes the disturbance that I did. So if I'm adding, let's say if I'm adding a reactant, my equilibrium is going to shift in the direction that is going to decrease that concentration of my reactant or get rid of my reactant that I just added. If I remove my reactant, the equilibrium is going to shift in such a way that it's going to make more reactant because it's going in the opposite direction of the change that I introduce. Let's look at some examples. Here is my, very well known now reaction. And I have heat in the reactant side, which means that this is an endothermic reaction. It requires heat to proceed in the forward direction. So it's an endothermic reaction the way it is written. If heat appears in the product side, then it's an exothermic reaction the way it's written. Let's look at use Le Chatelier's principle to predict the effect of the first case, increasing the amount of H2. If I increase the amount, which means I'm adding more product, Le Chatelier's principle states that if I add more product, the reaction is going to proceed in such a way in the direction that will remove the product. It's the opposite of what I do. If I'm increasing my H2, it's going to shift in a way to decrease the H2. The only way to decrease H2 is to make more product, because H2, to get rid of H2, I have to combine it with N2 to make NH3. That's the only way I can get rid of H2. Therefore, if I add more H2, I'm going to proceed, or the reaction is going to proceed to the right towards products, making more products. Let's look at if I decrease the amount of N2 or decrease the amount of any of my reactants. If I decrease the amount of N2, the reaction is going to proceed in such a way to make more N2. So once again, it's the opposite effect. To make more N2, there's only one way I can do that, is by taking NH3 and breaking it down. Basically, the reverse reaction will occur. The equilibrium is going to shift towards the reactants, making more reactants, which means it's going to shift towards the left. What happens if I remove some NH3? If I take away NH3, that means that the reaction is going to shift in a direction to make more NH3, because once again, it contradicts the change. If I remove it, it's going to make more. The only way it's going to make more is if it shifts towards the product, towards the right. If I were to add NH3 to counteract my change, the reaction would switch. It would change towards, it would basically shift towards the reactants, because it would want to get rid of the extra NH3 that I put in there. So it would shift towards the left. What will happen if I heat the reaction? Now, the way that I have added here, heat appears as a reactant. In an endothermic reaction, heat will appear as a reactant. In an exothermic reaction, heat will appear as a product. Now let's look at, if you think of heat as a product or a reactant, adding or removing heat will affect it just like adding or removing a reactant or a product. So let's look at it. If I heat the reaction, which means I'm adding more heat, I'm increasing the heat, which means I'm increasing, if you think of it, a reactant, my reaction is going to proceed in the direction that will counteract the change, meaning reduce that heat that I added. The only way to do that is to shift towards making more product, meaning shift towards the right. What if I increase the pressure? Now, what happened for pressure? If I increase the pressure, I know that it's going to be dependent on the number of moles of the reactants and of the products. If I increase the pressure, the system is going to shift in such a way as to decrease the pressure, because I'm increasing it. So the reaction is going to shift, try to counteract the change that I introduced, which is increasing the pressure. So it's going to try to decrease the pressure. Remember back when we talked about pressure, which means is force per square, force over area. My force is exerted in the gaseous phase, is exerted by the moles of the gas that I have. And therefore, the pressure, because it's the same area, I'm not changing the volume, the pressure is going to depend on the number of moles. The higher the number of moles, meaning the higher the molecules of gas, the higher the pressure. If I lower the number of moles, I'm going to lower the pressure. And therefore, I look in which direction will I have smaller number of moles of gas. As on my reactant side, I have 4 moles of gas, 1 for nitrogen and 3 for hydrogen, 4 moles. If these two combine, they give me only 2 moles of ammonia. So I have 2 moles on the product side. So I have fewer moles as product as I do as reactant. So if I increase the pressure, the reaction is going to shift to reduce the pressure. And the only way to reduce the pressure is if you reduce the number of moles. And to reduce the number of moles, the reaction is going to proceed towards the product because I have fewer moles of gas as product than I do as reactants. I have 4 here, but only 2 here. So fewer moles of gas, meaning less pressure. So the reaction is going to shift towards the product. What happens if I add a catalyst? Well, a catalyst does not affect the equilibrium of a reaction. What it does affect is how fast the reaction proceeds. It affects the reaction rate. The reaction rate, but not which direction it proceeds or the value for my equilibrium constant. So adding a catalyst does absolutely nothing to the equilibrium constant. It may just speed up the reaction, and that's typically what happens. But it doesn't have an effect on the equilibrium. What happens if I increase the size of the vessel? So now, if I'm increasing the size of the vessel, what am I doing? I am increasing the volume. What happens? We're talking about gases now. If I increase the volume, due to Boyle's law, we know that if I increase the volume, I decrease the pressure. As I decrease the pressure, I'm over here now. Here I increase the pressure, it shifted towards the products. Here I'm increasing the volume, which means I'm decreasing the pressure. The system, the equilibrium is going to shift in such a way as to increase the pressure. The only way that it can do that is if it increases the number of moles, because number of moles are directly related to pressure. I have a larger number of moles on my reactant side than I do on my product side. So if I decrease the pressure by increasing the volume, the system is going to shift in a way that will make more moles of gas, which will increase the pressure, and therefore it's going to shift towards making more reactants, and therefore it's going to shift towards the left. Practice a few of these. They're not very difficult. First, you have to ascertain the change that you're doing, and then how do you counteract the change? The harder parts are the pressure and the volume, these two, and maybe the heat. But if you think of the heat in an endothermic reaction on the reactant side, exothermic on the product side, so if you think of the heat as another reactant or another product, then increasing the temperature, adding heat, or decreasing the temperature, lowering the heat will cause the reaction to proceed in the exact same way as if you increase or decrease the amount of reactant or product. What is a practical application that in everyday life of Le Chatelier's principle that we all know? Well, we all know that we need oxygen to live, and hopefully we all know that oxygen transport in our body involves hemoglobin, it's a protein, and oxygen, obviously, in our lungs and in our tissue. Hemoglobin reacts with oxygen to form oxyhemoglobin, and actually it can bond up to 4 oxygens. And in the bound form, hemoglobin travels through the blood to tissue, and this is the reaction, And it's a reversible reaction. It proceeds in the forward reaction and in the reverse rate. If my oxygen level is high, so if I have a lot of oxygen, that will cause the reaction to shift towards forming oxyhemoglobin to get rid of the extra oxygen that I breathe in the lungs. So in the lungs, the reaction will shift towards binding that oxygen to form oxyhemoglobin, which is wonderful for us because that way we bind the oxygen. As oxyhemoglobin travels through our blood into tissue, the concentration of oxygen is low in our tissue because it's being used up for all the biochemical processes that are needed or is needed. Therefore, if I decrease the concentration of oxygen of my reactant, this reaction is going to shift towards opposing that change. So it's going to try to increase the amount of oxygen, the amount of reactant. The only way to do that is if oxyhemoglobin breaks down into hemoglobin and oxygen. And therefore, when oxyhemoglobin reaches tissues, it releases the oxygen from the hemoglobin and it forms oxygen gas and hemoglobin so that we can use the oxygen in our tissue. Once hemoglobin makes its way back to the lungs, oxygen level is high, so to get rid of the extra oxygen, it binds to hemoglobin to form oxyhemoglobin, and then it gets transported back to the tissue, back and forth, back and forth. So you can see why Le Chatelier's principle is so important to our bodies. It's just this is a practical example of how Le Chatelier's principle shows us which direction the reaction is going to proceed. And then lastly, let's look at what happens in high altitude when we have less oxygen at really, really high elevations. We know that the air gets thinner, so we have less oxygen. And if you're not used to it because you don't live there or because you have not acclimated, you might experience hypoxia, which is characterized by increased respiratory rate. You're trying to get more oxygen into your lungs, and you might have headaches or mental acuteness, etc., etc. All of these are signs of a lack of oxygen to the brain and to your body. Why is that? So let's talk about it. Well, here's our old friend Le Chatelier and his principle. Here's our equilibrium we talked about in the previous slide. We have hemoglobin binding to oxygen to form oxyhemoglobin. In higher elevation, you have less oxygen, which means you have removed some of your reactant. Therefore, what's going to happen due to Le Chatelier's principle is that the reaction is going to shift towards making more oxygen. So oxyhemoglobin breaks down to release oxygen and form hemoglobin. You can see then that the amount of oxyhemoglobin is smaller. That amount that goes around in the tissues is less than what it should be, and therefore you have less oxygen going to the tissue. The way we respond to that is by increased respiratory rate. You're trying to breathe faster to get more oxygen into your blood, into your tissues. Eventually, if you lived in that elevation, higher elevations, for a continued period of time, your body gets used to that. And how it does that, it compensates. It cannot do anything about the amount of oxygen, but what it can do is increase the amount of hemoglobin in your blood so it produces more of the protein. Once again, it increases one of the reactants, and therefore it's going to shift the reaction to making more products to get rid of that extra hemoglobin, free hemoglobin that's circulating in the blood. Therefore, your body can compensate that way and make more oxyhemoglobin to circulate in the blood. Okay, this is the end of chapter 13 lecture. You can once again look at all the embedded. So this time, instead of adding the extra links to JetNet, I'm going to embed them directly in these PowerPoint slides so that you can look at them directly. If you have any questions, don't hesitate to ask. Thank you.